towards the intercept, towards the true answer. Understand that? Now, do we want to derive it? No, it's 2. I think that's enough of the geometry to get you to see what's happening. If you want to derive it, come by my office, we'll derive it. So here's the formula for Newton's method. This is on page 243. X sub n plus 1 equals x sub n minus f of x sub n over the derivative of x sub n. Now, that looks a lot worse than it actually is, all right? Again, if you want to see it derived, I can do that. So let's take this example right here and let's start with our guess, all right? What was our guess? 2. X sub 1 is 2. The way this formula works is that if I want to know what this point is, x sub 2, x sub 2 will be what? So imagine that this is 2. If this is 2, that means n is what?
3.
No. If this number down here is 2, then n is 1. So that means x sub 2 will be x sub 1 minus f of x sub 1 over the derivative at x sub 1. Now remember the function we're working with here. What was the function? Was it x squared minus 2? That was the function we're working with? All right, so coming over here, because my initial guess was 2, this is what? 2 minus f of 2 over f prime of 2. I'm running out of space. I'm going to have to do this over here. So x sub 2 is equal to 2 minus, what is f of 2? 2 plugged into the original function, which is 2. Okay, over, and then what's the derivative of this? I didn't write it down. What was the derivative? I figured it was easy enough. 2x. So you plug in 2 into the derivative and you get 4, right? 2 into the derivative, you get 4. So you get 2 minus a half, which is 1.5. I'm going to go to a decimal now, all right? 1.5. Do you agree? So we started out by guessing that the answer was 2. One iteration of Newton's method, that's what we call it when we run this cycle one time, it's called an iteration. So one iteration of Newton's method got us from 2 to 1.5. Let's do another iteration. What's x sub 3 going to be? Well, by Newton's method, it's x sub 2 minus f of x sub 2 over f prime of x sub 2. See, we're using the answer we just got to get the next point. And what happens is that these x sub 1s, x sub 2, x sub 3 start to march closer and closer towards our true x-intercept.
When you reach 0, that's when you know
You usually won't ever reach 0. We'll get to that. When do we stop? Right? When do we stop? All right, so let's just plug in here. So this is equal, we'll need a calculator at this point. X sub 3 will be 1.5 minus, now we have to plug in 1.5 into our original function right here. So we're going to go 1.5 squared minus 2, right? What do you get? Y'all know what I'm doing or not? Plugging 1.5 into this? Yep, 0.25 over, now you plug in 1.5 into the derivative. So 2 times 1.5, 3. So you get 3. So now on my calculator, I'm going to do 0.25. I'm divided by 3, this right here. And so 1.5 minus, I'm getting like 0.08333 forever, right? It's repeating decimal. That's what happens.
Yeah.
So the question is, how far do I want to go out? You know? Well, let's go 1.5 minus 0.0833333. I'm going to go like 7 or 8 decimal places. I'm getting 1.416666, something like that. Now, what is the square root of 2 if you typed it into your calculator? 1.414213, something like that? Are we getting closer? Yes. So let's do one more iteration.
So it approaches it kind of like a limit?
It approaches it like a limit, yes. It approaches without necessarily having to get to it. So if I do x sub 4, I get, 1.4166. So how far do we want to go out? I mean, it's really, the more decimal places we go out, the more precise we're going to be. So I'm going to go out as far as, let's say that. And then now you have to take that answer, 1.416666, plug it into the function, so square it, subtract 2, and I'm getting like 0.0069426 or something like that, over then this into the derivative times 2. Do y'all see what I'm doing or not? Okay. So then 1.416666 times 2. This is 2.83332. Do that, subtract. I'm getting on the next, this is turning out to be 1.4142096. 7, let's just say. So look, I'm actually, like when I did it the first time, or not the first time, yeah, if we list out the numbers, let's list them out, just for fun. What was x sub 1? It was 2, right? So x sub 1 was 2. X sub 2 was 1.5. X sub 3 was 1.414666. X sub 4 is 1.414209667. And if I keep doing this, it's going to converge or get closer and closer to the true answer. So your calculator, what did your calculator say it was? 2.1. Yours stopped at 2.1?
Yeah, mine did.
Mine didn't. Mine went 3.562. So why did yours stop at 2.1? It's just you're right now, the way you have it set to stop at a certain number of decimal places. If you adjust that, guess what it does? It just goes further out into this. See, if I go look at from here, from x3 to x2, I mean x sub 3 to x sub 4, notice 1.414 didn't change. If I go again, I bet you the 2's not going to change. And the next time out, right, whatever's going to be next, there's going to be a 1. And so what happens is your calculator, when does it stop? It takes the difference of these two. It subtracts. Look, if you do x sub 4, let's do it right now, minus x sub 3, what do we get? Subtract those two. 1.414209. I'm getting something like 0.0004693. Anyone else get that? No? Did you get negative?
I got like weird. I got 4.5.
Oh, does yours have a little E thing on the?
Yeah.
That move the decimal over. That's what that means.
We got a negative.
You got a negative. Just take the absolute value. It doesn't matter. Your calculator is going to take the absolute value. What does that mean? What am I doing? What is your calculator computing here? It's saying I went one more step, right? And the difference between those two answers is this much. The next time, there's probably going to be another 0 here, which means right now I'm within, what, tenths, hundredths, thousandths? I'm within like 4 10,000ths, 4 or 5 10,000ths of the true answer. How close do you need me to be? Right? I'll go out as far as the computer has a built-in, it has a built-in to the programming how far to go. And it'll go maybe until there's 8 zeros. And then it stops. So your calculator actually doesn't know what the square root of 2 is. It knows it within a certain precision. That's all it knows. Does that make sense? That's Newton's method. Now, Newton's method works a lot of times, but there are times where it doesn't work. What is the problem we had last class? I just want to see if we even can. Remember the one I said we won't do it and Newton's method could get it? We were trying to set the numerator for derivative equal to 0. Yeah, does anyone have it there? Do you see how that algorithm is perfectly suited for a computer?
Yeah.
You put in input, that output becomes a new input, and it just cycles through so many times, right?
Yeah, that way it's just saying, what's saying costs more computer power.
That's right. Yep, operation counts and things like that, orders of operations. No, magnitudes of order, how many operations it takes to get to an answer.
Yeah. In order to you will need more power.
That's right. No? No one has it? X cubed?
I have 2x plus 6x.
Wait, what did you have?
4x cubed.
Is that what you
I had 2x cubed
Plus 3x minus 4.
2x cubed plus 3x.
3x minus 4.
Oh, plus 3x minus 4. That's what we were setting equal to 0? That looks more familiar to me. Yeah? Do you remember what the answer was? I went to the computer and got it.
About
0.5535.
X is about, what?
0.5535.
0.5535. Yeah, that was it. Okay. So let's see. This is what we did. I said, I can't do that. You can't do that. We can't do that, right? We went to the computer solved it. All right? Let's just see if Newton's method even gets us close. First of all, what's f of x?
the whole left side.
The whole left side, because it's already set equal to 0, right? So I just move everything. Do you have a comment? No?
Yeah, it was 4x cubed. It was 4x cubed plus 6x minus 4.
See, and what he was doing is he factored out a 2, so that 4 would actually become a 2, but we
Okay,
didn't factor
yeah.
out that 2.
Oh, yeah,
We
you
didn't?
did.
So yeah, the original one was 4x cubed plus 6x minus 4.
Yeah.
So
Okay, we'll go back to that.
we just changed our 4 to
Well, let's just see. Let's see which one gives us. We need to just work with. Do we agree that if I just put a polynomial up here that we can't solve, we'll try Newton's method? You said the original one was what?
4x cubed plus 6x minus 4.
But then if I change that to a 2. So you're saying I pulled out a 2 but forgot to pull it out on the other one?
Yeah, you need to pull it out of 4. You need to pull it out of 4. Negative 2, right?
Let me see. Let me see what you have written down.
So if you factor 2 out of that.
4x cubed plus 6x. Okay, all right, good. So let's change this to a 4x cubed plus 6x minus 4. I just want to make sure that the answer that I am going for is the answer to this. Okay, so according to Wolfram, or to my math program there, that should be the answer. So let's let's let the left side of this be f of x. Right, so f of x is 4x cubed plus 6x minus 4. I'm going to need the derivative to use Newton's method, right? 12x squared plus 6, and that's it? What do you want to use as a guess? All right. What I'm going to do is I'm going to create a function real quick here. 4x cubed plus 6x minus 4. All right. And then, so the way this works now, I just created a function. So if I say what's f of 2, it's going to do the computation for me. Understand? All right, so I'm going to create another function. I'm going to call it g of x, which is going to be the derivative. So the derivative was 12x squared plus 6. All right. With me? Here we go. So what did you want the guess to be? 1? Let's start it. X sub 1 equals 1. So how does the computer come up with a guess? Well, it can guess some things, right? I mean, and what it does is it tries to look for a change in sign. So like if you plug 1 into this, what do you get? A positive or a negative number?
Positive.
You get a positive. And if you plug in 0, what do you get? Negative. So it'll check like 0 and it'll check 1. It'll say, I had a change in sign. It's got to be between there. So it's going to go and take a guess to be 1. It could have used 0. All right, so let's see. X sub 2 will be 1 minus the function at 1 over the derivative at 1, right? Which is, let's see, the function, so I'm going to say f of 1 over g of 1. See, I'm cheating here. And in front of that, it's 1 minus that. Do y'all see what I did here? 2/3. 2/3. Hey, 2/3 is 0.666. Yeah? Forever? Okay. It's closer. So let's now get x sub 3. X sub 3 is 2/3 minus f of 2/3 over the derivative at 2/3. You understand the computational nightmare this is for us by hand, yes? This is why a computer's so good with this. So I'm going to take 2/3, I'm going to subtract f of 2/3 and divide g of 2/3. And it's going to do it as a fraction, but I think you would go to decimal by this point. 0.5662. No, 0.562. So this is going to be 0.562092. Understand? And then I could go again. I take that answer. I subtract from it f of that answer. In this program, the percentage mark means the previous answer. G of the previous answer. And I'm getting 0.55362. 0.553. Did I say 62? Yeah, 624. One more time? Okay, one more time. So percentage minus f of percentage divided by g of percentage. 0.553574. 3574. What was the answer that I gave you in class? Oh, 5535. We're there. Close enough, right? What do y'all think?
It's pretty cool.
It's pretty powerful.
My hand would suck.
It would suck by hand, which is why it's okay to turn to a computer, in my mind, to solve it, because all you're doing is applying Newton's method. As long as you understand the computer's not smarter than you or smarter than us. You know what I'm saying? The computer's just using an algorithm. That's all it's using. The fact that the algorithm works is what's astonishing, I think. Now, there are ways you can screw Newton's method up. Not every function can, you cannot get every function with Newton's method. All right, there are some that just don't behave well enough. An example would be something like let's say you had a function that did this, almost like a sine curve. And you were trying to find one of those x-intercepts in there. So what happens is you take a guess, and let me try and zoom in. I'll zoom in so you can see what's happening in there. Let's say I'm trying to find that x-intercept. And so I'm having this thing oscillating through here like this. Let's say like that. So you pick a test point, like a guess. So you guess this one right here. You go up, you take your tangent, and it spits you out here. And then you come here, and you grab that one, and that tangent line takes you back, spits you out over here. And then you take this one, and now that one, that tangent line takes you back here. And then you're up here, and then that tangent line takes you back. And what happens is because of the curvature of the function, it's spitting you back and forth all over the place, and you're never getting closer. So there are some limitations. But with polynomials, they behave well. And so we don't have to worry about this. And Newton's method is very effective. So there are other methods on top of Newton's method where they account for this, and they attack it in different ways.
When will we learn that?
You won't take, well, if you take courses in like numerical analysis, which would be like junior, senior level math courses, then you would do more, yeah, okay, yes. So yeah, numerical analysis. You learn different algorithms and, yeah. What?
Is it a heavy proof class?
No, it's a lot of theory in that class. Yeah. I had to write, that's where I really had to, I was forced to learn how to code things up in that class. This isn't coding, by the way.
What was the hardest math class you taken?
Functional analysis. Yeah.
Did you make it?
I got an A in it, but it was the hardest one I ever took. Yeah, it was hard.
Can you use Wolfram to write programs? Like, can you write programs in that?
Wolfram Mathematica is the brains of Wolfram Alpha. So the website Wolfram Alpha, when you send something, it sends it back to the kernel, which is the brains of this program, basically. And that's where it all does the computation.
So you could use that language to write a program? Like
Yes.
in
Mm-hmm. Wolfram Mathematica, yeah, it's all C+ based.
Okay.
Yeah, C++. It has so many built-in functions, you really don't need to do a lot of coding. But, I mean, you can do like do loops, for loops, while
where
loops.
it's like you input something and then it goes through all that and it gives you the output?
Yes, absolutely. Yeah. I think I already wrote a code for it. I just didn't bring it up.
Okay.
I'm sure, yeah. You got me wondering now. I'm pretty sure I have it here. Let me see. Let me just search in here for Newton's method. Newton's method. Yeah, I had already prepared something here, but I don't know why I didn't.
My physics teacher, my senior year, he told me he used Excel.
Mhm.
He'd write a program for his homework, and then he'd just enter his homework problems and get all the answers from his Excel
Oh, really?
program.
Yeah. 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 I mean, use it as a tool. Yeah, this is code I wrote for this already. So like, what was the problem we just had? X cubed. No. 4x cubed plus 6x minus 4.
Yeah.
And then,
It's 40 obviously.
yeah. And I'm not sure, R is where I start.
We did X.
M is 2. Okay, X, we started with 1.
Yeah.
Let's see what happens here. 0.5. 0.56029. I think that was only 2 iterations. So let me go 5 iterations. Yeah, so there's 5 iterations. This one's similar, except I did it where it's going to show you each of the outputs. So q plus 6x minus 4.
N equals 5.
Where is it?
It's on the first.
Okay, there we go. There you go. So that's x sub 2, x sub 3, x sub 4, x sub 5, x sub 6, right? And that's what you're asking, right? Could you just code it up in this language? Yeah. See, it's just a for loop. That's all it is. For I equals 1 until I is less than or equal to 1, increase I by integers. Do this operation with r being 1. And then this is the thing this is the actual computation. That's the Newton's method is right there. That's it. That's Newton's method. And then print out the answers. So if you wanted to, so look, if you went out to like 12, and then let me say, what is this? Print M200. That's now going out 100 significant digits for each one of the answers. That's too far. There, that's 30 digits for each one, decimal places. So now you can see, like, look, I did the first 12 iterations, and look at, where do they change? Oh, look, after about the what? This is this first iteration, no, first iteration, second iteration, third, fourth, fifth, sixth. After the 6th iteration, they don't change. 30 decimal places out. I think that's usually good enough, right? So you want an algorithm which we would say converges fast. This converges fast compared to there's more primitive methods. The most primitive method there is called the bisection method, which is you just take, like we just said on that last problem, the answer was in here. It was 0.55 something. And we could check 1. When we plug in 1, we got a positive number. When we plugged in 0, we got a negative. Bisection method just cuts that interval in half and says, okay, now look at 0 and 0.5. Does it change? And then you check, and it wouldn't change. Then you say 0.5 to 1. Does it change? Yes. And then it cuts that in half. And then looks at that one and looks at that one and just keeps cutting in half. That works, but it's slow. It's a high operation count. That one's a lot more efficient. All right, well, we have about 10, 15 minutes left. I do have enough time to at least introduce us to what will be our last section, our last concept, really, of the class. No tears, no crying. 4.7,
Tears started in spring.
and anti-derivatives. Yeah, we're going to talk next class about the final.
What day is the final?
Wednesday.
Is it Wednesday?
I believe it's
That's right, because my class before this, our final's next Monday, so ours will be on Wednesday. But I believe it's at 12:30.
It is.
And that's not my choosing. That's so it doesn't overlap with other finals at different times, and All right, antiderivatives. So this is where we start to get into what Cal 2 is going to be about. And it's basically reversing everything that we've done as far as derivatives in Cal 1. And so I like to just motivate this with just a pretty basic example, right? What if I tell you that the derivative of some function is, let's say, 2x? Can you tell me what that function was? X squared, right? How much thinking did that require? So if the derivative is this, then I think we would all agree that x squared would work. Is that the only answer?
No.
No? You want to give me an example of another one that would have worked?
X squared plus 1.
X squared plus 1 would have worked?
How about x squared plus c?
X squared plus C?
Yeah, any constant.
So any constant. Do you all agree with that? It wouldn't matter what constant I add. This would be x squared plus nothing. This is x squared plus 1. I could do x squared plus 1,000. I could do x squared minus pi. Any constant I have attached to this, right, through addition or subtraction, wouldn't matter. That, when you take the derivative, would go to 0. Yes? So even though this is a specific result and this is a specific result, this right here is the most general answer, right? So it looks like that would be the case no matter what. No matter what we ever look at, if we're trying to go backwards, we should always have this concept of a constant there. Look, if I give you a different one, f prime x equals cosine x. What is f of x then?
Sin x.
Is sine x, but it could be sine x plus 2, sine x minus 5, anything, right? So sine x plus c again.
Plus or minus c.
Okay, so plus or minus c. C can be any real number, positive or negative. Okay, so this constant, it's understood this constant is any real number. So I'll put that here, where c is any real number. So of course, if c is a negative number, then this would be subtraction. Make sense? All right. How about this one? If find little f. Negative cosine x. Good. So you have to be careful with this, because if you just put cosine x plus c, what's the derivative of cosine x? Negative sine x, right? But you want it to be positive sine. So you actually have to put a negative in front of this so that the derivative of cosine is negative sine, but then you hit it with a -1 and it becomes positive sine, right? You all see that? Be careful with that. So that brings us to, well, I'll give you one more. If the derivative of some function is equal to 1 over x, find the function. Natural log, right? The natural log? That's just because of your experience with it, right? The derivative of the natural log of x is 1 over x. We've been through this, yes? Okay. So are you already kind of getting the idea that the better you are, the more familiar you are with derivatives, the easier it's going to be to go backwards?
Yeah.
Yes? All right. I think today we'll just get into just thinking through some stuff, all right? I don't think I'm going to put anything formal up here. Let's just think about some situations. How about this? If the derivative of some function is, let's say, x to the 5th power, what's the function? Think about what happens when we're going from the function to its derivative, right? And it's a power like that. What did we do? I mean, what happens when you take derivative of something that has a power? What happens to the power?
Bring it down.
It comes down by 1, right? So if we're going to go backwards, what do you think is going to have to happen?
Goes up by
It's going to have to go up by 1. Yes? So whatever this is over here, it's probably a good guess to think that it was x to the 6th to start. Would you agree? But if I take the derivative of x to the 6th, do I get x to the 5th? No, why not? The 6 would come out, and I don't have a 6, right? So how could I offset the 6? Put a fraction in front of it, 1/6. Right? If I put 1/6 in front of x to the 6th, then when I take the derivative of this, the 6 will come out, it'll cancel out, it'll become a 1, and then take the power down, I'll have this, yes? But I could have thrown any constant on the end of that.
So if that's the case, what's the constant?
Any number. It can be anything.
Yeah, but
So this is a good, you're asking a good question here, because look, before I started talking about this, if I give you a function, I come up here, I say, hey everyone, you see this? What's the derivative of that? Everyone would be like, oh, derivative of that is x to the 5th power, right? And that means if I graph this function, if I graph that, which looks something like this, then this would represent the slope of the tangent line everywhere, right? What we're doing is different. We're saying, we know the slope of a tangent line is this. What function does that come from? And it turns out that this one works, but if you move it up 1, that one works, and if you move it up 2, it works, and if you move it up 3, it works. You move it down 1, down 2, down 3. If you move it up a half, move it down a half. Doesn't matter how far up or down you move it. All these curves, all these functions right here, all have the same derivative. All right? So when we go from a derivative back to a function, we don't get a single function as an answer. We get what we consider to be a family of functions. Right? It's not just every function. It's a specific type of function, but it's the whole group of them. It's every one of them shifted up and down that you could think of. Does that kind of make sense? Yes? All right, so let's try something a little more challenging. How about the square root of x? Now everybody knows the derivative of the square root of x, right, is 1 over 2 root x. But what's the antiderivative? What is the backwards? Going from that back to its original function. So how are you getting that?
I made x, I put x to the 1/2.
So you put 1/2 out here,
Yeah,
okay?
I added 1.
So you're thinking the power is going to go up by 1 in the new answer, right? So I'm going to move this down a little bit. So you're saying that the power's got to go up by 1, so you added 1 to that to get 3 halves.
And then I took the reciprocal of that and made it the coefficient.
And so you know that when that comes out, you don't want it there, right? Because that's a 1 in front. So you put the reciprocal of it in front. Will that work?
Plus c.
Plus c. So this would come out, hit here, become a 1. We subtract 1 from 3 halves, we get that. That'll work. And that's the answer. We'll just leave it like that. There's nothing, we don't have to do anything else with that. All right, how about this? We're almost out of time. So I'll just, this will be a problem to humble us, all right? That seemed pretty easy so far, right? So what if I just throw something simple like that on the back? Or you know what, let's make it cosine. What if I do that? That seems harmless enough, right? I mean, x squared by itself and cosine, right, by itself seems...
There's multiple ways you can do it, right?
Well, can you look at that and see it? I mean, so what's the problem? I mean, what do you...
Undo the product.
We're trying to undo something that looks like, I mean, at the end we get a product, don't we? You can't do this, right? Just look at this. You cannot just say, all right, what's the antiderivative of x squared? Well, it's 1/3 x cubed, right? And then say, oh, what's the antiderivative of cosine? Say sine. Because if you think it's that, then just try and take its derivative and see if you get that, and you're not going to. Because you'll have to do the product rule here. And when you do the product rule, what will happen? You'll get, let's see, 3 comes out, you'll get just x squared, but then times this one sine x, but then plus, now derivative sine x cosine x times 1/3 x cubed. Do you see that? This is the derivative of this. Is that that? No. No, you're way off. So how do you go from this backwards? And that's something we won't be doing in this class right now, but it's just to show us the challenge that we have of going backwards. It's not easy. I'll ask the computer to do it for us. Oops. Because I'm out of time. I'm going to ask it to... because I don't want to leave you hanging there. Integrate x. I could do that by hand. It's not hard to do. It's just a little time consuming. The antiderivative of that is 2x cosine x minus 2 sine x plus x squared sine x plus c. That's the that's the backwards. From here to here is this, right? And you can check it. Take the derivative of that yourself. Well, if you're going to check it, what would you have here? Product rule here. This one's clean. This is another product rule here. So you'd have product rule, and then when you put it all together, guess what you get? X squared cosine x. So that's what you spend the first 4 weeks of 4 to 5, 6 weeks of Cal 2 doing, is learning how to go from like this back to there. So next class, what we'll do is we'll keep it a little more under control. We'll deal with, hey, how do you deal with things just like that, an x to a power, and then some problems that have a little more complexity to them, but we will not be able to handle this. Yes.
Is there like a standard method, or is it just like start guessing?
No, the thing about the Cal 2 is that there are 6 techniques that we use, but it's not like, in Cal 1, we've learned pretty much there's only certain rules, right? You have power rule, powers come down, right? We have product rule, quotient rule, chain rule. That's it. There's pretty much nothing else out there. With antiderivatives, you don't have rules, you have methods, and you try and use these methods. But there's no like, oh, sure, that's chain rule, just do this. It's not that. Yeah. Yeah, because if this problem right here is done a certain way, if I change this to e to the x, it's done the same way, but there's a major difference within the work. There's something majorly different inside when you do it that happens. It's, hey, stay tuned. Cal 2 is coming your way at some point.
So I had a question